It's not even a survey, really. It's more of an introduction to the world of descriptive complexity theory and these extremely weak and very interesting logical reductions. Traditionally, of course, you all know the framework. We've got NP completeness via a decision problem. It's NP complete. It's a polynomial time reduction from any NP problem to that problem. Of course, a polynomial time reduction is, as you well know, an algorithm that runs in polynomial time where yes instances map to yes instances and no instances map to no instances. And there are many other notions of reduction. We have polynomial time Turing reductions. These are the many-one reductions. We have one-way log space reductions, where we're only allowed to use log space on the machine and the head can only move one way. We have polynomial time truth table reductions, which are essentially equivalent to rounds of parallel queries, and there's lots more in the literature. Now, most notions of reductions are pretty wild in this sense. If we have some source input, different source inputs of the same size can yield target outputs of, well, significantly, possibly different sizes. Okay, so if I have a reduction from, I don't know, clique to Hamiltonian path, and I stick in two graphs of size n, well, I've got no control over the size of the graph that pops out at the other side, beyond that it's bounded in polynomial size of the input. Different source inputs might yield the same target outputs. It's quite possible. And the existence of an atomic element, by that I mean, if we're talking about graphs, an edge, say, whether this edge exists in my target structure, might depend on a very complex property of the source structure. You might have to do quite a bit of computation, okay, polynomial time amount, in order to decide whether some edge is actually present in your target graph. And it might be preferable if we could better control reductions. And perhaps this might help in essentially developing tools for proving that certain reductions cannot exist between certain problems, i.e. lower bound results. This is the theory behind it anyway. Let's go back to the roots. So those of you who were here yesterday, probably all of you, have seen everything on these next couple of slides yesterday. In fact, I feel like the guy on The Sopranos where he says, just when I thought I got out, they dragged me right back. Well, I'm going to drag you back to yesterday and this algebraic framework. Okay, in 79, and in fact, these two slides are worth putting up just to advertise this paper. One of the most beautiful papers ever, Valiant's 1979 paper. Anyway, he proposed an algebraic framework for the study of polynomials over some fixed field, K. And the definitions are as follows. So a P family is a sequence of polynomials where the number of variables and the degree is polynomially bounded in terms of n. And the total complexity of some polynomial, well, it's just the minimum number of arithmetic operations that you need in order to compute the polynomial via some straight line program. We had all of this yesterday. And this yields the complexity class VP, consisting of all of the P computable functions, where the total complexity is polynomial. So if we want to step up to get an NP analog, or a non-deterministic analog, Valiant defined the P-definable family of functions if we have a P-computable family, G, such that Fn in your family of interest is the sum over all zeros and ones plugged in here of the function Gn. And we get our complexity class VNP. And so now we've got VP, VNP. We want to look at a reduction to try and obtain completeness results. Well, a polynomial is a projection of another polynomial. If we take our other polynomial and we plug in the x's accordingly and maybe throw in some elements of the field, and we can compute f of n using g of m in this way. And finally, we get that a P family is a P projection of a P family G. if there's some polynomially bounded function, so that if you want to compute f of n, well, we take g of t of n is some polynomial, and g of t of n is a projection of f. Finally, we get the notion of VNP completeness. If any p family is a p projection of g. So this family is VNP complete if any p family is a p projection of g. So that's Valiant's framework. And he showed, as we heard yesterday, that the permanent is essentially, it's VNP complete if your field doesn't have characteristic 2. And we also saw yesterday that the determinant is different in that using Gaussian elimination, for example, we can show that computing the determinant is in VP. And again, as we heard yesterday, Valiant's hypothesis that VP is not equal to VNP is the VP is not equal to VNP. It depends up to a point on the field. But that's essentially paraphrase of a lot of what we had yesterday. And so what I want to do essentially here is I want to show how this notion of projection, Valiant's notion of projection, translates through logic into uniform projections. And so in order to do this, I'll explain how we use logic to classify problems and develop logical translations, essentially uniform versions of Valiant's P projections. And then look at some developments using these very weak logical reductions in complexity theory. Actually, is there a glass in here or a cup anywhere? Thanks. Oh, it's all right, Raoul. It's all right. Thank you. Okay, so that's what I want to essentially do in the talk. So let's turn now to descriptive complexity theory. What's that all about? Well, traditional complexity theory, of course, classifies problems according to how easy it is to solve a problem using a machine. Whereas in descriptive complexity, we are going to be interested in how easy it is to define a problem using logic. And luckily for me, because I spent a lot of my time messing around with these things, there's an intimate relationship between logical definability and traditional computational complexity. And adopting this logical approach, just in very raw terms, it gives us extra things to grab a hold of. It gives us lower bound techniques or non-definability techniques in terms of logic that don't really arise in the traditional setting. Games, Eric Fraser games, 0-1 laws and such like. And it gives us logical concepts to grab a hold of, again, that aren't apparent in the traditional setting. Like we can look at the quantifier prefix of some first order or second order logical formula that we might use to describe a problem. We might look at the arity of the reductions as a notion of difficulty. We might look at the syntax of the defining logical sentence. And essentially, adopting this descriptive approach gives us new classification parameters that don't arise or don't exist in the traditional setting. So how do we go about defining problems using logic? First of all, we need the notion of a problem. So a signature for me is going to be a finite tuple of relation and constant symbols. So this signature tells me what I'm talking about. For example, it might be this signature, where E is a binary relation symbol and C and D are constant symbols. And a finite structure over this signature, or a signature in general, consists of a finite domain, which I always take to be an initial segment of the natural numbers. It consists of a relation of the appropriate arity, so here, a binary relation, over the domain for every relation symbol of the signature. And for every constant symbol, I've got to specify a constant from the domain of the structure. So finite structure over this signature here, we can think of it as the domain tells us what the names of the vertices are. The binary relation gives us an edge relation on those vertices. and C and D essentially pinned down to designated vertices. And we denote the size of a structure, a finite structure, just by the number of elements in the domain. So those are the objects, if you like, of study. Now I've got a funny little thing that I'm not going to go into in too much detail, but I always assume that every structure comes for free with a binary relation symbol called suc, or successor, and two constant symbols, 0 and max. And that in every finite structure A of size n, there's always this binary successor relation and two constants hanging around that interpret the binary relation suc and the constant symbols 0 and max. So that this successeration looks like this, consists of those pairs, 0, 1, 1, 2, dot, 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 n minus 2, n minus 1. And the constant symbol 0 is 0, and the constant symbol max is n minus 1. Okay, so every finite structure has this thing for free. Okay, I'm not going to go into too much detail about logical aspects of this, but we can use it, this successor relation, in our logic. And we say that such a finite structure has a built-in successor relation or an ordered structure. Okay, so those are the objects. Now a problem is an isomorphism closed set of finite structures. So just you ignore the successor relation and 0 and max. I mean isomorphism with respect to the normal symbols of the signature. So for example, here's a problem denoted HP, and it consists of those finite structures over the signature consisting of a binary relation E and two constant symbols C and D. That is digraphs with two named vertices, so that there is a Hamiltonian path in the digraph from the vertex C to the vertex D. And that is a typical problem. It's a set of finite structures that's closed under isomorphism. Here's another problem. I'm using these two examples because I'm going to stick with the vocabularies or signatures later on. Here's another problem. This time my signature consists of two binary relation symbols, P and N, and it's a satisfiability problem. And essentially I think of my finite structures as sets of clauses as follows. The literal xi is in the clause cj, so my Boolean variables are indexed from 0 to n minus 1, and my clauses are indexed 0 to n minus 1. And I have that the literal xi is in the clause cj, if and only if pij holds in my structure. And the negation not xi is in my clause cj, if nij holds in my structure. Okay, so now there may be empty clauses. I don't treat those as real clauses, I just ignore them. So that's how we might code up SAT and HP as isomorphism closed sets of finite structures over some signature. And of course, SAT is such structures where there's a satisfying truth assignment. Now, Fagans' theorem, which is essentially the focal point of descriptive complexity theory, is from 1974 and characterizes NP in terms of logical definability. A problem, that is one of these isomorphism closed sets of finite structures, is in NP if and only if it can be defined in existential second-order logic, even when we haven't got these funny successor relations hanging around. So you can just forget about the successor relations and 0 and max. And Fagans' theorem says that a problem is in NP if and only if it can be defined in existential second-order logic. Now, existential second-order logic is the logic where you're allowed to introduce new relation symbols and you existentially quantify over those relation symbols before having the matrix of the sentence described by a first-order formula. And here's why SAT, for example, is in NP according to Fagans' theorem. Here's my existentially quantified prefix of new relation symbols. It happens just to be one relation symbol T, which is unary. So I'm talking about a set of elements of my structure. And this, in English, essentially reads, there exists a set of indices such that for every index y, if there exists an index x such that xx is in clause cy, or not xx is in clause cy, that is, the clause is non-empty, then there must exist some index such that either xx is in clause cy, and x is true in this set, or the literal not xx is in clause cy, and x is false. So that's how we use existential second-order logic to define the satisfiability problem, where I've defined satisfiability over the signature P and N on the previous slide. Here's how we might use second-order logic with a built-in order to define the Hamiltonian path problem. Remember, you don't need the built-in order, but I've included it here just to let you see how it works. Essentially, I'm saying, okay, there's a new relation, P. It's going to be a binary relation on the elements of my finite structure. And essentially, what this top line says is that P is a matching from 0 dot 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 to n minus 1 to 0 dot 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 n minus 1, so that the 0th element is C, the last element is D, and if x prime follows x in my built-in order, then, and the vertex matched with x, y, and the vertex y prime matched with x prime, there must exist an edge from y to y prime. So essentially what I've done is reorder my vertices so that there's a linear path from C to D, which is what I want to show that this path exists. So I'm just saying there exists a path from C to D that takes in every vertex of the graph exactly once. And I can do that in second-order logic, in fact, without using successor, but I've used successor here just to let you see how you might use this built-in successor to define problems. Okay, so we've got our setup. We've got our logical world. We haven't really gone into logics that very much, but we've got a hint at how we use logics to define problems. We know what a problem is. Now we want to compare problems. Now, traditionally, of course, we would take our source structure, graph or whatever, and we would build, via some polynomial time algorithm, a target structure, so that yes instances go to yes instances, no instances go to no instances, and such like. If we want to logically reduce one problem to another, for example, satisfiability to HP, then what we've got to do is we've got to define an instances of our target problem, HP, in terms of an instance of our source problem, satisfiability. So we've got to have come up with some way of defining a tau structure, where tau is the signature binary relation symbol E, C, D, constant symbols, in terms of a tau prime structure, where tau prime is the signature consisting of two binary relation symbols, P and N. And of course, we have to do this so that yes instances, no instances, dot, 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 dot. And here's the mechanism by which we build translations. So I'm going to say what it means to have a first-order translation from one problem to another. So I need an integer k and distinct variables, two k-tuples of variables, x and y. And for every symbol of the target signature, I need a formula that describes the relation. So for example, in my target signature, I have a binary relation symbol E. So I need a formula that essentially is going to describe, well, what's here are the edges of my target structure. And what resource am I allowed to use in order to define this set of edges? Well, I can use the first-order formulae involving the symbols of the source problem, which is satisfiability, along with, of course, zero max and the successor. And also, I've got to specify constants. And in order to do that, I specify two k-tuples of constant symbols from my source signature. Okay, so here, the satisfiability problem doesn't have any constant symbols, so these constant symbols will be 0 or max. Okay, so that's the first setup. I've got, for every relation symbol, I've got to just come up with a formula that's going to define that relation. And for every constant symbol in my target signature, I've got to come up with tuples of constants from the source that is going to tell me what this constant is. And given that, then I can now just say exactly what my target structure is in terms of my source structure. So my source structure is A, and the target structure, the translation according to these formulae, well, the domain of my target structure is going to be k-tuples of elements of the source structure, because we've got tuples here of length k. And the edges in my target structure will be all of those pairs of k-tuples u, v, so that when I plug u and v in as x and y and interpret accordingly, the formula holds. And of course, the constant is just going to be the tuple corresponding to this tuple of constants. And this constant for d is going to is the tuple corresponding to this tuple of constant symbols. Okay, so given this formula, and given my instance of satisfiability, I can use this formula to define a set of vertices, k tuples of the elements of my original domain, and set of edges, and two vertices, C and D. And if everything works, that is, if my source structure is satisfiable, if and only if my target structure is such that there's a path from this vertex to this vertex by following these edges, then I've got a first order translation. And the resource I've used is, well, first order logic. I used that logic to say things about the target structure. And also I allowed a certain number of variables in my tuples in order to describe the target structure. And that's the arity of the translation. Let's have an example. So let G be a digraph of size n, designated vertices C and D. And suppose it's an instance of the transitive closure problem. So normally I'd want to know whether there's a path from C to D. I'm going to build an instance of the complement of the two satisfiability problem. It's a very simple reduction. So if I have an edge ij in my digraph, then I'm going to build the clause Cij, not xi, xj. And also going to have the clause consisting of just xc and the clause not xd. Just let's do a quick check to make sure that this rough and ready description of a translation is does indeed take yes to yes and no to no. Well, suppose that there isn't a path from C to D in my source digraph. Well, what do? Well, I just essentially make all of the black Boolean variables I'm going to set to be true, and all of the white ones, that is all of the vertices, so that I can reach D via a path. I set them to be false, and it's not difficult to see that this is a consistent, this is a satisfying truth assignment for my instance of satisfiability. It all makes sense and it's well defined. On the other hand, if I have a path in my source structure, there's no way that I can make these clauses satisfiable, because going along the path from C to D, it'll screw up that assignment. Simple little undergraduate exercise there. But I want to describe this translation using logic, using my logical framework. So what I'm going to do is I'm going to use, it's going to be an arity 2 translation, so I'm going to have pairs, tuples consisting of just pairs of variables. And what does this first clause say? It says, well, if there's an edge from y1 to y2, and let's suppose that when I interpret y1 is equal to I and y2 is equal to j, so I'm saying that there's an edge from I to j, and also I need that y2 is equal to x1. So x1 is j and x2 is j. Am I making a mess of this? Then essentially what I'm saying is that for this to be true, it will only be the case when this edge exists, which is what I want, and xj, which I interpret as xjj, is in clause cy1 I. Okay, it's a bit of a meal of that, but that essentially tells me when positive literals appear in these types of clauses. I also want this special clause consisting of just the positive literal xc. So I want xcc is in the clause cc. And also, I want to tell you when the negative literals appear. And in exactly the same way, I can describe when the negative literal, not xi, appears in the clause cj, and also when we've got this negative literal xd appearing in a clause by itself. So quite simply, I can use two very simple formulae, first-order formulae, in order to describe my target structure in terms of my source structure. And consequently, S is the translation of G in this framework. In fact, even more so, I haven't used the full power of first-order logic at all. There's no quantifiers there, so this is actually a quantifier-free first-order translation. And so that's our framework. So now we say, okay, well, do complete problems exist under, I don't know, first-order translations, quantifier-free translations, or whatever for NP? And yes, they do, even on unordered structures. And indeed, on ordered structures, there's a whole range of complete problems via quantifier-free first-order translations for different complexity classes, NC1L, loads of them. Okay, and Anuj proved, this is slightly off topic, but he proved a very strong result that tells you essentially when complexity classes might have complete problems via quantifier-free first-order translations.
Is there an actual example of a class that has complete problems with respect to time or log space reductions, but not with respect?
Oh, I don't know. No. So yeah, no.
Okay, we don't have the order structures in our
Yes. But yeah, if you throw in order, then you're in the machine world, essentially. Okay, so as I've noted, our reduction wasn't just first order, it was quantifier-free first order. And in fact, if you look even closer, given any fundamental bit of S, remember S is an instance of satisfiability, and by fundamental bit I mean whether some literal appears in some clause. You know, you kind of get more fundamental than that. Given any fundamental bit of S, this bit, it doesn't depend on something really complicated involving the source digraph and the constants and whatever. All it depends on is one fundamental bit of G. So for example, whether not x1 is in the clause C13, according to this translation, all it depends upon is whether one edge exists in your source graph. And this gives rise to the definition of quantifier-free projections. And these are the sort of uniform versions of Valiant's P projections devised by Neil Immerman in the early 80s. So quantifier-free projections, a quantifier-free first-order translation where of a very strong, I guess, syntactic and semantic form. We can write this quantifier-free formula as a disjunction of conjunctions, where each alpha I is actually a conjunction of atoms and negations not involving symbols from my signature. So it might use the successor, it might use 0 max, it might just be is x equal to x or x not equal to x or whatever. So x not equal to y or x not equal to y. But there's no constant, there's no signature symbols in there. Moreover, the different alpha i's are mutually exclusive. Okay, so we can't have some assignment of values so that two alpha i's, i.e. alpha I and alpha j, are true at the same time. And also, each beta I is atomic or negated atomic if it appears. So you can think of the betas as being the signature literals. And you can think of quantifier-free projections as follows. Let's just stick with digraphs for ease of visualization. Suppose that your source structure has size n. And you know if you show your target structure, it's size n to the k, if the arity of the translation is k. So great, we've got some sort of consistency. We know exactly what the size of our target structure is going to be. Depends only on the size of the source structure. And as we're just talking about digraphs, we want to know the circumstances as to when an edge of the target structure might be there or might not. Well, if we fixed n, the size of my structure, and I just look at translations according to this reduction on structures of size n, either this edge is always present because one of the alphas was true. An alpha doesn't depend on the signature symbols of the source structure, so it's going to be true for every source structure. Or maybe this edge is always absent because none of the alphas are true. Of course, the alphas don't depend on the symbols or the relations or whatever of the source structure. Or maybe it's just going to depend on one literal of the source. Because exactly, if an alpha is true, exactly one of the alphas is true, and you look at the beta, and that's your literal, and it will tell you whether this edge is present or not. And it's really difficult to imagine a weaker notion of reduction, where you've got this consistency and where an essential bit of your target, all it depends upon is one bit of the source. Okay, so really we can think of our quantifier-free projections as, well, let's fix n. So consequently, we know exactly what the vertices are going to be. They're tuples of elements from 0 up to n minus 1. And there's going to be edges that are always there, like that edge, irrespective of what the source structure is. And there's going to be pairs of vertices where there is no edge, irrespective. And otherwise, edges will be labeled with literals. And in order to decide whether your given satisfiability instance, what it maps to, the instance of Hamiltonian path, all you do is you plug in the literals from your satisfiability instance. What you then get is a directed graph, not a label directed graph, because all of the labels have either been retained, been removed because the edge is being killed or not. And then you have a look at the resulting digraph. Is there a Hamiltonian path from the source to the target? And that's how these things work. So for example, with that description there, maybe I've got this structure. These are just toy examples to show you how this works. Maybe you've got this source instance of satisfiability. Well, this edge wouldn't exist because the label isn't true in the structure. This edge would exist because the label is true. This edge would exist because the label is true, because P31 isn't in the relation, and so forth. So you plug it in, and you'd have a look, and yeah, there is a Hamiltonian path. So your instance of satisfiability must be a yes instance. here's a situation where when you plug everything, well, you've got no path from the source to the target, so that's going to be the instance of satisfiability is a no instance. So these are very powerful, or very, very weak reductions. And quite remarkably, and much of this stems from Neil Immerman, is that lots of standard complexity classes, not only do they have complete problems via first-order reductions, not only do they have complete problems via quantifier-free first-order reductions, but they have complete problems via these extremely weak quantifier-free projections. Okay, so just let's reiterate, what have we got? Well, this quantifier-free projection from SAC to HP, say, for every n, there's a labeled digraph that tells you everything you need to know about the reduction for structures of size n. And this sequence of labeled digraphs can be uniformly generated. In fact, the description of these digraphs comes from the defined in quantifier-free projection. We'll return to this in a moment. So that's the basic framework. We want to look at logical definability in comparison with traditional complexity, computational complexity. We develop a notion of a logical reduction, and we start to prove things like we do in traditional computational complexity using our logical notions of reduction, in particular these extremely restricted notions of quantifier-free and quantifier-free projections. So let's have a look at what we might do with these reductions. So let's go back to Fagans' theorem. So we got any problem in NP can be described by a sentence of this form. We have some new relation symbols of whatever arity, and then a first-order matrix that essentially describes the formula. So we could say, okay, well, it turns out the transitive closure is complete for non-deterministic log space via these quantifier-free projections. And anything first-order definable is in a non-deterministic log space. That's easy. Consequently, what I can do is replace this formula phi by an equivalent formula of the form transitive closure with a quantifier-free projection embedded. And this enables me to essentially reduce this problem described by this formula to essentially a labeled digraph where the labels are R labels and labels from the source signature. So that, well, how does this work? If I've got some source structure, I kill the labels using the source structure, and what remains is an R-labeled graph, and essentially I know by construction that my source structure will be a yes instance of my problem if and only if there exists an assignment of true and false to the labels so that what results is a digraph so that there's a path from the source to the destination, the target. Okay, what I've just said there is that this second order formula can be massaged into a labeled digraph. Remember, it's a second order formula defining any problem in NP. So any problem in NP can be reduced so that on structures of size n, there's a labeled digraph that describes the reduction. And so that if I want to find out whether my instance is a yes instance, what do? I plug in the literals from my source structure, and that will kill some of the edges and retain some of the edges. And what remains are some R-labeled literals. And in order to decide whether it's a yes instance or a no instance, I want to try and find an assignment of true and false to these labels so that there's a path retained of edges. So for example, in any R assignment, I can never have those two edges at the same time, because if I make R12 true, this is going to be false, so this edge disappears. If I make this R12 false, this is going to be true. So you've got to look, and that's where the trick is. And so this is what it boils down to, is just by knowing the transitive closure is complete for quantifier-free projections, this problem automatically, just about, is NP complete. An instance is an edge-labeled digraph of the source and the target. And my S instance is a truth assignment that results in a digraph where there's a path from the source to the target. So we can use quantifier-free projections to completeness via quantifier-free projections to obtain new complete problems without even working at all. Now, there's nothing special about transitive closure. You can take any complexity class with a complete problem via quantifier-free projections that contains first-order logic, plug it in, and you'll get a labeled structure, or you'll get a new NP-complete problem involving labeled structures of whatever your chosen signature is. Let's skip over that because I'm running out of time. And in fact, this is quite interesting because why don't we say, okay, well, using quantifier-free projections, we can get lots of labeled structures that, depending on the problem chosen, characterize NP. And let's look at the structure of these new models of computation. Can we use these labeled structures as models of computation? Okay. And well, why not? You know, essentially, binary decision diagrams are, or what used to be called branching programs, are labeled structures of type. And there might be mileage in looking at labeled structures as computational devices and using completeness via quantifier-free projections to give us some idea of the power of these new computers. What time is it? Oh, we're in a bit short. Now we can also generate automatically, once we've got completeness via quantifier-free projections, it's got to be quantifier-free projections, problems for the polynomial hierarchy. Take the second level of the polynomial hierarchy, sigma P2. Now this can be characterized by second-order formulae where you've got an existentially quantified prefix of new symbols with a universally quantified prefix of symbols and your first-order bit. Now we're going to apply exactly the same technique, but we're going to observe that we're going to get labeled structures where just doing exactly the same thing. So any problem in sigma P2 can be described by a labeled structure so that there'll be some R labels and some S labels. And I want to find an assignment so that there exists some truth assignment on the R's, such that for every truth assignment on the S's, something is true. But we can do more than that. Let's just consider this part of my sigma 2 formulae. That defines an NP problem. And satisfiability is NP complete via QFPs. So what we can do is we can plug satisfiability in here with quantifier-free projections describing the reduction. And what we get is we get labeled instances of satisfiability. So we'll get conjunctions of disjunctions, but instead of being literals, they'll be labeled literals. And we'll be looking so that for every assignment on these Y's, what results is something that's satisfiable. Well, actually, we can massage this labeled literal to the conjunction YX. And what you automatically get, and this is it. All of this is for free. You get all of the canonical complete problems for the polynomial hierarchy. And you need quantifier-free projections in order to make all of this work. Obviously, if you use some other notion of reduction, it's not much work to come up with it. But all of this comes for free with QFPs. Okay, so this is my last little bit now. So that's just two little nuggets of the usefulness of QFPs. In the early 90s, Zimmerman and Medina asked this question. They essentially said, okay, we've got Fagans' theorem, and we can define any NP problem via an existential second-order sentence. What is it about this sentence that makes the problem NP complete? It's in NP, but what makes it? Is anything we can grab a hold of structurally that makes the problem NP complete? And they provided an answer, not entirely satisfactory, and certainly it's difficult to ascertain their answer from what I've written here. But they proved that the problem is NP complete via first-order projections, not quantifier, first-order projections. If and only if the problem can be written in existential second-order logic, then this is a very rough description of their normal form. If they had, if the defining formula is a disjunction of two conjunctions, where beta p is first order and appears positively here and negatively there, and the second part of the first conjunct is essentially a sentence that looks like a description of independent set. I don't want to say anything more about this. And this second conjunct here is anything you like, any second order formula. So essentially what they did, they said that, you know, if you want to know that if whether your NP definable, sorry, if your existential second order definable problem is actually NP complete, if you can massage your formula so that it has this normal form, then the answer is yes. And it's an if and only if. Intuitively, what this says is that any NP complete problem can be defined by a disjunction where essentially the first disjunct characterizes something as hard as independent set, and the second disjunct characterizes the rest. Okay, this is very, very intuitive. So intuitive, I don't get it myself, but there we are. But what they did is they had this characterization, and what they did, they wrote down just the defining existential second order sentence of, well, I don't know, here we are, directed Hamiltonian circuit. They just wrote it down, existential second order logic. And what they then did is they syntactically messed around with the formula so that they reduced it to this normal form and said, oh, great, therefore my problem must be NP complete. And these are the sort of manipulations that they used to prove NP completeness. They had a lot of operators that preserve NP completeness. So all of these operations, when you apply them, if your problem's NP complete to start off with, then when you fiddled around with the formula, what remains will be an NP complete problem. And you know, some of these manipulations are quite involved. But that's how it works. They had these operations, and they fiddled around, and they proved syntactically, just by writing down the description of those problems in existential second-order logic, that they were actually NP complete via first-order projections. This has recently been extended so that not only can we do this with NP, we can do it with those complexity classes. And we can also develop new, possibly nicer normal forms where we don't essentially just rely on this independent set-like structure. But the key to the whole approach is syntactic manipulation, just fiddling around using operators that you can dream up that preserve NP completeness. Okay, I'll skip over that. And this general approach essentially evolved into a more general question. Essentially, okay, well, can we automatically find reductions just between problems, you know, arbitrary problems? And this was tackled in 2010 by Neil Immerman and his students, I guess. And they did this with respect to quantifier-free reductions. So they were trying to automatically, by automatic, I really mean automatic, using a tool. They wanted to automatically prove reductions between problems. But there's a slight difficulty in this. Well, if you have two problems, omega 1 and omega 2, definable in data log, then the problem of deciding whether there's a quantifier reduction from one to the other is complete for the second level of the arithmetic hierarchy. It's undecidable. So this is problematic if you're trying to develop a tool that you want to provide good results. So they restricted things, and they said, okay, let's use the arity as a parameter. So you can restrict the arity. You can restrict the number of clauses in your projective formula, the size of the clauses in your projective formula. And if they do that, okay, it drops the complexity, but it's still co or complete. But then they said, okay, not only, but we don't necessarily want to ensure that yes instances go to yes instances, no instances go to no instance for every structure. But let's just say, okay, stick the parameter n in, and you just want to be sure that it works for all structures up to size n. And then they obtain a decidable problem. And essentially, the key appeal of, it should be first order projections, projections are key here, is that you can easily enumerate these things and they can be written in symbolic form, and that gives rise to SAT solvers or QBS solvers and whatever. And Neil and his colleagues developed a tool called Reduction Finder, and from their paper, Reduction Finder finds many simple reductions between a wide class of problems, including several clever reductions that the authors had not realized existed. I guess is that a definition of a clever reduction? Oh, I didn't know it existed, so it must be clever. Let's skip over that, shall we? Anyway, but here's a sample of the sort of stuff that they got up to. So they performed that many searches on a database of 87 problems. And of the however many pairs of distinct problems, they found reductions between quite a few of them. And a lot of these reductions essentially were extendable by transitivity. They found that so many pairs were irreducible, couldn't be, and there were not that many pairs remaining unfinished. And so you can say, ooh, can we do something really good here? What they did is they tried to prove the Imam-Shillop-Cheney theorem by looking for automatically a reduction from complement of TC to TC, and they couldn't do it. And also, similarly, with regard to Reingold's theorem, they looked for a reduction from symmetric transitive closure to deterministic transitive closure, and they couldn't do it. This has been picked up recently by Jordan and Kaiser. They have a reduction finder called DE. And they say that, in principle, you can prove the Imam and Shillop-Cheney theorem by if you can find what turns out to be an arity 8 quantifier-free projection. Problem is that with their tool, they struggle with even arity 3. So there appears to be a really big blow-up. If you're looking for reductions involving tuples of 2 variables, yeah, it's okay. But tuples involving 3 variables, life gets tough. And what they did was they were still working on this. They're just looking for, better and better implementations to try and creep this arity up. So that, I guess ultimately they want to say we've proven the Imam and Shillop-Cheney result automatically. Does that mean it's not a clever reduction? I don't know. But anyway, let me stop there because I'm just about out of time.
Questions, comments?
So you said for this automation, they have to restrict the sizes of the structures, not just the arity. So in this, I'm just trying to understand what they're doing in an automated way. They find some reduction that works up to a given size n, but they sort of then extrapolate and say, oh, let's assume it always works, or what do they? So what's?
I haven't looked at the nitty-gritty detail, I have to be honest. But that is. I'm not too sure. I'm flying blind here.
There's the undecidability result.
Yeah, I know.
You can't do it in general, and then you're saying they're doing something in an automated way.
Yeah, that's what I gathered by reading this stuff. I'm sorry, you'll have to have a look at the data.
So, this element data result you're talking about, it's somehow the theorem of some kind of complete proof system for finding reductions. So if there are two problems such as one reduces to the other, there's some sequence of manipulation.
Oh, I have no idea, absolutely no idea. Everything is so ad hoc. I think, in their original paper, they had a collection of operators, and those operators sufficed for them to be able to come up with their 30-odd manipulations. But, yeah.
So I guess I have a similar question. Is there any kind of intuition what reductions might be easy to find and which ones would be hard? You mentioned those 2 problems which were hard, but...
Well, I only mentioned those 2 problems because they are sort of substantial results that conceivably might be automatically discovered in such a framework as proposed by these guys. But so I just plucked them out as problems that they couldn't cope with. But they might.
Are there any more comments or questions? Let's thank you again.